we'll just go through sort of the different types of concrete floors, and so it applies to concrete floors in concrete framed buildings, and it also refers to concrete floors that you put into a steel frame. So this helps you get an appreciation of all of the different types of floors there are. So we'll be looking at precast, we're looking at poured into place, so you've got in situ, concrete, and all of those span a different amount. And so if you really want the furthest span, you've got like a dome, but in terms of a floor, if you had a precast T-shaped floor, then you could use that. You'll find that the most common type that we have is just a flat. There's a flat slab with beams underneath. That's what we predominantly use. In steel, they'll use these precast. So we'll go through each of these types. I've got like a couple of videos just to try and show you what concrete floors are all about. So again, it's called in situ concrete when you pour it on site, and precast when you do it. It's Latin. So if you imagine, like this is a false floor, but we've got that's a precast floor. But let's imagine that this is a concrete floor that we're going like that's on the first floor. What we would have to do is put up our scaffolding, and you've got two different terms for formwork. There's false work and formwork. The formwork is the material that the concrete is cast against to form its shape. But to try and get this floor up to the right height, we put in this false work. Contractors all call it formwork, but that's if you see the word formwork and false work, then that's what it's talking about. And there's a number of different products that you can use, and these are all mechanical. Like you can get hydraulic ones, you can get bespoke ones that are set at a particular height. But these are lifted to place, screwed to the right height, and then they use, in this case, it's timber beams, and there's a piece of timber that the concrete is cast up against. So if anything, you just got to make sure that this formwork is strong enough. Now you don't do the design for the formwork; it's the contractor. But there are some like little guides on how to check. So in terms of overall for this topic, in terms of an exam, get an appreciation of the different types of floor and how they're put together. I'm not bothered if you can remember, whether it's called a main bearer or a second bearer type of thing. So you've got the first type where, if you can imagine, it would take a carpenter, or they call them chippies, quite a while to create a timber form to go around if they were going to cast it in concrete. So what they do is that they buy in some bespoke scaffolding and formwork, and there's like Aero Deck, and there's a company called Perry. Is the main company that does the larger. Perry is yellow, it's very expensive. There's Aero Deck, which is like blue, which they use in the northeast a lot. But these are people who supply this formwork and false work. In terms of the cost of a building, if it was a concrete building, so 100% for reinforced concrete, the whole building, 60%, well, in between 30 and 60%, depending on how much formwork you've got to put in, goes on the formwork that you put in place and then take out the way. So, up to, if you've got a really, really complicated building, 60% of your costs just got into putting everything into place, so you can cast the concrete, wait till it goes off, and then you remove it. So you'll find that when it comes to reinforced concrete buildings, the schedule, trying to get everybody in the right place at the right time is really important. one, to try and sort of speed up the time, because you've got a lot of people on site who are making up all of these. And plus, this formwork, they put it in place and they don't keep it there for, like, do we know how long it takes for concrete to go off? Have you covered the concrete in materials yet? I think maybe it's week next week, 16, if you're covering concrete. But in terms of concrete, it increases in strength over days. And what we tend to measure is day 7 and day 28. And by day 28, your concrete is at the stress that it'll probably be at for the rest of its life, like near to. It does go up, but once you work out what the 28-day stress, so you make your cubes and you crush them and you can tell what strength it is. And we design with concrete up to 50 newtons per millimetre squared. But we don't want to keep this formwork in place for 28 days, because that means if we were doing a floor with the same formwork, we'd be doing a floor every month. And if it was 12 floors, it would take a year to do. So what you'll find is that contractors find out when you can remove the timber from the concrete, because if you pull the timber away, it pulls away the surface and it just wrecks the surface. Like, that surface is okay. Looking at that precast, it looks like there's a few little air holes. Like that might be just like the paint effect, but if you've got a final concrete finish, you've got to make sure that your formwork is not going to be damaging it. And they say that once it's round about sort of 2 newtons per millimetre squared, that you can peel away the formwork. That's called striking. I believe the word striking comes from, it's a bit like where they hit the timber to actually free it from the concrete, and then they remove it. And because they're trying to move the formwork around really, really quickly, what they do is they use a lot of these drop head props. So this is our prop here, and it's the outside of it is holding up the beams, and that's holding up the timber that is connected to the concrete. So they put in place, wait until the concrete reaches enough strength so it can support its own weight. Some contractors talk about the concrete going green, has like a green sort of glaze over the top. When that point occurs, and they can make cubes, and they test the cubes after, say, 7 days to try and figure out how strong it is. Then they remove these beams and the formwork, and they just leave the props in place. So here's an example of a drop beam. So that there, it's actually holding up the formwork up against the concrete. Then they drop the outside, and the outside is all of the props stay there, and they move all of the formwork just somewhere else, and then they use it just because it's so expensive to use when they're putting together a concrete frame or a concrete floor. And the leaf, so we've got like beams and timber holding up the concrete. They drop that, they leave the props in place, and then you've got to leave the props in place until the concrete has reached sufficient strength to hold itself. And what you'll find is that they're going to be building another floor on top, so they've got the weight of the floor being supported by these props, and then if you end up putting another floor on top, you've got to make sure that this is strong enough before you remove all of these supports. Another technique is table formwork, and what this is about is that they put together formwork in a table shape, and they wheel it into place, they push it up to the correct height, then cast the concrete, and when it's gone off, they then just drop it down and then just wheel the table form to another place, lift it up, cast it. So compared to the first one, that's where the workman would put together all of the individual bits for every location, where, you know, to try and speed things up, you can use table formwork, where it's just all one piece and it's just moved around. You can use this when you've got a building that is very, very similar everywhere, where you've got a floor slab across a massive area. So there's an example of 3 table formworks underneath some concrete that is cast. And once it's gone off, then they can lift that and take it up. The nice thing about these table formwork is that you can have safety rails, you can have anti-slip areas, so that it's always safe for the people who are doing the work on the floors themselves. So that's table formwork, and there's a photo of it. In terms of formwork, you can have timber. Cost expensive to use joiners, so you have sort of like plastics, aluminium, steel, lots of different types. You know, if the lighter it is, then the less weight is going to be on the building when it's being constructed. And like I say, the Perry type is yellow, and the Aerodeck is blue. That's how people identify it. Perry is a bit like when we come to look at cladding. A lot of people buy Kingspan, which is just expensive cladding that you put on a building. Perry is expensive. I'll give you some text just to what to work through. Just to give you an appreciation of these different types of ways of putting floors together. So the formwork, again, false work, your beams, and then you've got your pieces of timber that your concrete is resting upon. Now, concrete sticks to the timber, right? It just soaks into the timber surface. So when you pull the concrete off, you can pull off the top surface, and you can repair it. They just get like there's these bags that have all little steel parts in, and they're Hessian bags, and they just put some concrete in, and they rub it. They call it bag it to repair the surface of the concrete. But what you do when you have your timber just before your concrete arrives, you spray or you paint on a mould oil. A mould oil. There's companies like Sika who provide this. Like, the contractors will put it on because it's for their benefit. Otherwise, the concrete ends up sticking. But it's like a release oil. And when you make concrete cubes, you'll find that you'll use a release oil to make sure that you can get the concrete cube out of the actual plastic mould, otherwise it's stuck. Now, reinforced concrete, when you're with me next year, my last module with you, more of an R. Whenever you're designing something in concrete, we're applying a load at the top, and what we have is that the concrete is good in compression, and in the top we've got compression, and in the bottom is in tension. And what happens, the concrete snaps in tension first. Concrete has about 10% tension. So what we do is we put our steel in, and the steel fails first. That's what we want. We want the steel to fail first, so it stretches slowly, which gives us enough time to get out there. We don't want the concrete to fail, snap suddenly, because everybody just dies straight away. But there'll come a point that the load is so massive that in the steel, which is 500 newtons per millimetre squared, because the concrete is around about 35 to 50 newtons per millimetre squared, once you get a certain load, you'll find that the steel is perfectly fine at the bottom and it's going to fail in compression. It's going to be crushed. So you can put steel in the top also that deals with the compression. Now it's important to make sure that there's a gap in between the outside of the concrete and where the steel is. The steel has to be protected. If it rusts, if it fails, then the concrete will fail first. So we have to protect it. Like in America, they just say that this distance here is going to be 50 millimeters before you get to the actual steel. Like in the UK, we've got like 8 page worth of calcs that we'll do next year to try and work out. And what that takes into consideration of is that, you know, if it's touching the ground, so if that was resting on the ground, and you've got all of these chemicals that could be trying to get through the concrete, as soon as they touch the steel, they could deteriorate it. Or if what you find is that if you design a concrete building here compared to at the beach, so at the beach you've got a lot of water and you've got a lot of salt soaking into the concrete, so you need like a larger area before you get to the steel. And you've got to make sure that your steel is in the right place. And usually this is what we check as civil engineers. The reinforcement will go in, then we go with our little tape measure and measure this just to make sure that it's like sort of 50 mil. So before they pour the concrete, how do they make sure that the reinforcement is going to be at height? And they've got all of these different types of spacers. So there's like a steel ring spacer that they put in between the two levels. So you put your little spacer there. There's a number of different types. Just lifts it up to 50 millimeters. And then this gap here might be about 100, 200 millimeters. So you can buy ring spacers of different depths that you put in, and then put your next layer of steel on top. Then when you you tie it all together, and you pour your concrete on top, and your steel stays there. So there's an example of our steel reinforcement, which there's some on the bottom, some on the top, and there's a steel spacer. When you come to work out the steel, you have to work out an area of steel, and you know, usually slabs, the load is horizontal in both directions, so you tend to have some form of grid. If the load is not that great, you can buy this mesh, such as like A393. Like we put a lot of that into concrete drives to stop the concrete from cracking, and that's just steel spaced at 393 millimeters, like apart. So you learn a lot about different types of reinforcement next year. You've got you can buy little bags of little cement spacers. Again, you can have plastic ones, then ones with cement. What builders do around here, like local builders, they'll get a paving slab, which is about 50 mil, and just smash it. And because it's concrete, it's perfectly fine, so they put it in there, and then they pour the concrete all the way around. So you can use whatever means, as long as it's, again, it's just trying to protect the steel. It's all sort of tied up also. But it gets really complicated when you look at something like that. You know, you've got your drawing, and you know, have a search for a reinforced concrete slab drawing and see what it looks like. And then you're supposed to read that drawing, and then supposed to say, is it the right amount of steel there? It's very, very difficult to tell. There's a lad on the second year at the moment. He was a steel fixer. He says that civil engineers don't know how to check steel. He says all they used to do is just come along measure what the cover is, then they used to look at the complexity and think, yeah, that'll be all right. That's what he found as a contractor. What do you reckon that is? Yeah, so it's just like a little box. So imagine you pour your concrete, covers the whole thing, and then you think, oh, bugger, we need a hole there. So you can either get a diamond drill, so that's a drill that has some diamonds on it, very expensive, and that will cut a hole through, or you can put a piece of timber or polystyrene just to try and sort of create a hole. Then once the concrete's gone off, you just stamp through the polystyrene, you end up with a hole all the way through. And we've got some bars there. They are called starter bars that you would be putting your column in place. But you can see how, we've got all of the surfaces going through. There's a larger void there. So it's a good idea to try and create all of your voids before. So you've got, the quick thing is putting these table formworks into place. So you bring it in, lift it up into place, and it'll be covering sort of this flat area. And they can be moulded to try and create a shape, a pattern shape within the concrete. It just becomes a little bit more expensive when you start to build around things, and you need a lot of where you're trying to fill in the gaps with the timber. So here's we've got our table formwork is in place. So there's one there, there's one there, and there's one there. But as soon as you start to go around columns, then that's when you're going to get a chippy or a carpenter involved, who will then have to try and fill the gaps to make sure that all the concrete's not going to go through. They have to use like expanding foam and different techniques to try and stop all of the concrete sort of dripping through and down below when they actually pour the concrete. The contractors designed the formwork. We don't do that in this module, but it's a bit like an excavation where you've got the concrete weight gets transferred. If this was concrete being poured, and you've got the water, you've got the load also pressing against this formwork, and you've got to make sure that this formwork is strong enough to hold everything back, and make sure that any false work is fine to keep the concrete back. Table formwork can be called fly-in formwork. This is where, so we've got our table form here. So again, it's put into place, lifted up, your concrete is cast. When your concrete goes off, then you can get, via your crane, you can pick up your table and just move it to the next level. Again, even though you've removed the main formwork, until the concrete's fully gone off, you will have to leave props in place to make sure that concrete doesn't fail. There's an example of a C-frame that is used to pick up the table formwork. That's another one. So props, normally left there 28 days. However, you can get concrete admixtures that you can add to the concrete, which either speeds up how quickly the concrete hardens, or can slow down. So they usually put in a plasticizer to allow it to flow easy, and then they put in an admixture for it to go off quick, so that they can then remove these props and take them elsewhere. You don't have to look at the different types of admixtures. These outriggers are just creating place for the people to work on when they're casting the concrete. You've got to make sure you keep everybody safe. And you can buy bespoke fences and nets, and you know, if you're buying the bespoke ones, it's a lot more expensive than say putting up scaffolding. But it all depends on, you know, the company that you're working with and what deal they have. But you've got to make sure that these people are safe. That's part of your job. In essence, you're like a policeman just walking around. And a lot of times when you walk around, work stops until you go, and then everybody gets on with whatever they were doing. Concrete. We could pour it 100 meter cubed per hour. Just keep on pouring it and pouring it and pouring it. But what you'll find, due to waiting for concrete trucks to arrive, they get stuck in the traffic, instead of 100, you tend to get round about 30 meter cubed per hour. You know, you could be waiting for the crane, if that's how it's delivering the concrete. And so at some point you have to stop your slab, and then like the next day, like cast your next slab. And there's a number of different types of joints that you have, and they're all like sort of like about sort of 15 sort of millimeters, and you've got movement joints. Now this is where your concrete, when the sun is shining on it, that concrete can expand. If there's not any movement joints, it will hog or sag. So you need a bit of a gap for it to expand into. Now we usually make these gaps either using like a weak timber, or you've got these or you've got this polystyrene that you can put in that allows the concrete to contract and expand into. And the top you tend to put in a mastic in there, which is just like a sealant to stop the water from going in. That's what you need. But so you know, if that was on the ground, then that would be fine. The concrete could be moving. But if that there was the floor above, you know, if we've got some load there, you can't have a gap there, otherwise it's just going to fall down. So what you need is a piece of steel which allows the expansion to occur. So there's going to be no movement vertically, but we need, if you join the two pieces of concrete together with a reinforcement bar, it's going to hog or sag. So this bar is stuck in the concrete. So as you're finishing off your concrete, you put in it's these white bars. Then you can paint like a layer onto this reinforcement, and maybe have like a little cap on the end, which is like this is yellow here, which when this concrete is moving backwards and forwards, it's not connected to the steel, so therefore it can move freely. And what this does, it doesn't allow any vertical movement, but allows horizontal movement. So we've got an expansion and contraction joint. These grey bits, they're just really, really long spacers. Again, the spacer is just so the light grey is again just trying to give this like 50 millimeters before you get to the bars. And you can see that the bars are also are below the top. Some of these bars in the top there. That's an example of what can happen to concrete if you don't have movement joints. That's why when you walk along the road, and it's a concrete road, very noisy concrete roads, but you will see that there is a gap, a movement joint every so often. It's the same in buildings. We talk about brickwork and blockwork. And, I can't see any on that building, but there's movement joints on every building. If there's not, you'll end up with cracks. This is just showing the detail of a concrete wall, and then you have some starter bars which will connect the wall to the floor slab. So you've got to make sure that it's all connected.
What determines the length of the starter bars?
The length of the starter bars is based upon the Eurocode 2. So next year you get a detailing guide. So you've got everything about how long these should be, or if you've got a really long floor slab and you've got a steel bar, but your steel bars aren't the full length. But so what you have to do is you have to lap them together, and then you have to tie them. And then you've got rules about how far you should lap them together, and there's rules about how often you space your bars. There's a lot of detail. Seems to be a lot of detail just for a simple reinforcement and concrete. So we've got our starter bars for a column. So those bars are coming out of the slab, and then what we'll do once they cast the slab in place, they tend to leave a little raised area called a kicker. Kick her, and they put reinforcement in place for the column, and then they cast the column. So they're starter bars. Again, there's another example of boxing out, which can be timber and polystyrene for surfaces. Just explain what this is. So in terms of normal steel bars, you put them down and you just leave them. In the concrete, what this is pre-tensioned or post-tension steel. So it's exactly the same, reinforced concrete, except the steel is stretched. And we'll look at the purpose behind that in a moment. But this is some people doing some post-tensioned concrete slabs. Now, just to give you an idea of why they use this, is, you know, when you have a concrete beam, like this is like a little bit of structural mechanics, you know, you have your neutral axis all the way through the middle, and the concrete at the top's in compression, and it's in tension at the bottom. So at the top of, if this is the stress, and that was 0, normally you've got the maximum amount of compression which the concrete is coping with, and then as you come down the beam, slowly at some point it becomes tension. So this is why we put our steel within there. So this is our tension. Now, if you put some additional steel in there, and you put it under tension, so that when you let go, so that, you know, like when you pick up a load of books and you push it together and lift it up. So you put the whole concrete in, so you get some steel, put that into tension. What that does, it adds. When you add that to what you have with the steel and the concrete, you end up with a concrete slab that is that has little compression. So that would be our tension and compression. So if you add some steel that's in tension, if you add enough, it raises the neutral axis. So essentially, just everything's in tension, and everything's been held by the steel, and you don't need as much concrete. So the benefit of that is that whenever we have like concrete and steel, you might have like a 400 or a 300 depth slab. Tensioned floors can go all the way down to 100 thickness, and so the big difference for this is that, you know, over 10 floors, you're losing, well, you're gaining sort of 300 mil every floor. And if you've got a restriction on the height of the building, then you're going to get more floors in if you use these tension floors. The system that you were shown there was the phrase net system. So just have a look up like that one. There are other systems like the McCalloy system, and the Magnell and Gifford and Udall system. So there's lots of different systems, but they're all quite similar. And the purpose is, like with normal concrete, well, one, you're trying to reduce the height of the floor. Two, like I've talked about, you get the full strength of concrete after 28 days. Wouldn't it be nice if you could get the same strength that you wanted in 28 days in 24 hours? Well, by using pre-tensioned concrete, you can get the same strength in concrete by putting it under tension. So once your concrete's reached a certain strength, you then tension the bars, and it squeezes it together. And within 24 hours, you can get the same strength as what you would have with normal in situ concrete, where the bars aren't tensioned. So this is the anchor block that they put at one end. So they put the anchor block here, and then you saw them thread some bars, and you know, in this case it'd be sort of five bars going through. Each bar could be made up of sort of 7mm wire. It can go much larger, but a lot of the wires, like say between 3 and 7 mil, and it's plain carbon steel, goes all the way through. So we've got our, just to give you an idea of, you still have got your normal reinforcement in the top and bottom, but we have this additional steel that we put in, that is tensioned. So we've got our anchor block, one end, and then we have these tubes that your tension steel is going to be going through. So there's like a sock or a tube that's going to be going all the way through the concrete, and you're going to attach the the steel at one end, and then what we're going to do once all the concrete's cast, we're going to pull the steel using like a stressomatic jack. When it's pulled to the correct tension, the anchor then squeezes the concrete and creates a tensioned floor. So again, you've got the normal reinforcement from in situ, and then you've got your tensioned cables that are inside of these. And your slab could be one-way spanning or two-way spanning. If it's two-way, it means that you've got your tensioned wires in two spans. So this is a close-up showing there's 4 bars of twisted wire going through the anchor block, going into this tube here. This tube has is filled with grout afterwards. So once the steel's been tensioned to protect it, they fill the whole tube with grout, so there's no chance of these tensioned wires failing. So this is before the concrete's going to be poured. This is our anchor block. One end is the anchor block, other end is your steel bars are just crimped. You get like a machine that splays the bars, so these are fixed at one end and then pulled at the other end. That's a crimping machine. Once the concrete's cast, they pull the wires and then they fill the tubes with grout. That's like a little diagram when you look at it on blackboard of how the anchor block works. But once they're pulled through, they don't go back. That's a finished anchor block which they then close off with concrete. If you have got pre-stressed or post-tensioned floors, you have to note where these are. If you because it's under tension, if you search for demolition of a pre-tensioned building, because the steel's in tension and the concrete is stopping it from is under compression. If you had a demolition excavator sort of cut through the concrete, the steel would just snap and it fires to the concrete about. If you look on YouTube, there's a few videos of concrete being fired because the steel has been under tension. But if this was just a normal reinforced concrete floor, you could cut a hole in it, and it wouldn't really matter if you hit a bar because of the amount of steel and how it's operating. Because it's normally not in tension, but this stuff is. So they mark it to show don't cut here. You can cut there, but this is where the actual bars are going in. This is where they've done an X-ray of the floor to try and identify where the tensioned bars are before they do some work. This is like for doing like a condition survey. You saw a picture of the jack. And each set of bars are tensioned to a set amount to make sure that it's catering for the dead load and the live load. There's an example of a failure where the steel bars are pulling in, but the concrete's not being able to hold back. It's not strong enough, so it's failed there. There's another example where the concrete's failed. where they had to repair that. That's an example where they had the bars were curved rather than going straight across the floor. If they were curved and put under tension, the bars have pulled through the concrete sideways. So there's a failure. So they say avoid curving if possible. You can curve it, but you've got to make sure that you've got tendons in place to make sure that it's not going to fail. Like so. Right, all the concrete floors that we've done to date are where they're poured in situ. Precast is where they're cast in a factory, and they're used in steel. So this building here, we've got our steel beams, and then we've got our precast floors, and they're about 1 metre wide and about 3 metres long. They're resting on top of the beam itself. Now, either we'll see that these precast slabs can either be solid or they can have holes in. They've got reinforcement in them. The ones that have hollow precast slabs, they're lighter, so therefore can span further. They've still got sort of steel through. And you don't design these, you just go to a company and just say, I've got a gap there to there, and I'm going to have like a certain type of loading because it's a university. Can you specify a floor? And they tell you what type to have. And you can see here that the precast could rest on the bottom flange of an asymmetric beam. It could rest on the bottom half, which looks like it is on there. These ones in this building are resting on top of the top flange. This is just an example plan where you've got precast concrete units with a 60mm topping on top. The span direction is this way, so we've got our steel columns, our steel main beams, and the concrete slabs are spanning that way. So on here we've got the size of the beams. And, it doesn't say what type of precast slabs they are, but that's like a typical drawing. Here's a building under construction. So again, hollow precast concrete slabs resting on beams. These have got holes in, which allow services to go through. Companies such as Castelli produce them. But we saw when we looked at the Phoenix building, the steel frame goes up, and then all of your concrete slabs are all sort of put down into place, and with a crane. Normally, the precast slabs go down, and the design is where the concrete is composite, is connected to the steel frame. So you have to connect it usually with shear studs. So this is our concrete marathon truck, a little bit like a steel frame, put into place. This is just showing that you've got a little bit of netting just in case they drop the plank, but it's more really just to protect the people if they fall through. You can slightly see 3 dots representing the steel that's going through there. That's in tension. And put the concrete under compression. Once the floor is in place, this one here hasn't got a screed on top, so that the floor is deep enough to cater for the load. This is a false floor, like an access floor. I think we cover access floors in another later session. But you've got these little pedestals, little struts that you then have your floor put on top of. We like access floors just so that you can have like the ventilation system in, which I'm guessing is all of these silver circles. And then also you could have a lot of access points for plugs and in computer. There's an example of solid planks, not as wide, but they're really long. And you've got your steel beams, you've got your shear studs. What the shear studs do when you put your grout screen on top, it connects the floor to the steel beams, and it becomes like a diaphragm, which makes the building all rigid. This is them delivering the screed on top of. The design also can have reinforcement bars across different planks to hold them together should the design need it. The precast is probably the most popular. The other type that is quite popular is wriggly tin. And this is where you have a steel beam, and imagine that you have some steel sheeting that when you put in between the two beams, then you cast your concrete on top. It's like formwork, but the formwork stays there. It stays in position. You don't remove it afterwards. The steel acts in tension, and the concrete above is in compression. So this is a steel beams, and then they're just going to be putting out each of the. So there's different profiles that you have for the wriggly tin, usually some different depths. So steel frame is put out. You usually have covers at the end, so that when you pour your concrete on top, it's not going to flow over the sides. You've got to make sure that the detail around the column is all closed off, so that the concrete doesn't seep through. So the concrete is poured on top. And there's an example of where the concrete is on. It hasn't been cast fully across the whole lot, but you can see the concrete. There's some mesh reinforcement in the concrete to stop it from cracking, and then you've got your wriggly tin underneath. That's the underneath of the wriggly tin. In terms of when you protect beams from fire, your main beams normally have to be covered in that intermittent paint that we covered when we looked at steel. Because the concrete protects the wriggly tin, it doesn't have to be sprayed with intermittent paint. This is a picture of somebody putting the shear studs through the wriggly tin.
Stud welding is also a form of arc welding. In composite structures, these headed studs form the connection between the steel structure and the concrete. Using a handheld unit, the arc is ignited via contact between stud and flange. Then, the arc heats the stud face and the flange, forming a weld pool. The ceramic ring acts as a form, as protection of the weld pool, and keeps the heating and cooling time under control. Although the process is standardized to a large extent, close control and good workmanship are essential. The main causes of weld defects are moisture, dirt, or rust on the metal contact surface. A special form of stud welding is through-deck stud welding. The stud is welded through a thin steel plate used as formwork in a composite structure, later to be covered with concrete. For quality control, stud welds can be tested by bending. Because cold cracking may occur some time after welding, this bending test should be executed at least 1 day after welding.
The good thing about joining the concrete floor to the steel is that you can reduce the amount of materials that you need in the building by 50%, so you don't need as much material. So this is the reason why you've got these shear studs. So here's my favourite pictures of Wrigley tin and shear studs and some reinforcement. The reinforcement might be part of the design of the floor. A lot of times it's put in just to stop the concrete from cracking when it's deflecting. This image here shows some spaces that are lifting getting to the right height so that you can put the mesh on top at the correct height. So it's like something like 100 millimeters above the Wrigley tin. There's another example of a box form being made so that when you cast the concrete stops there. You have a nice hole all the way through. You can see a little bit of this expanding foam that they've sprayed underneath, so that when they pour the concrete, it's not going to go down the sides of the concrete columns. There's a polystyrene hole, and you find that whenever you have a corner with concrete, whenever you have concrete going around a corner, you always have to put diagonal bars in just to stop cracks emanating from the corners. Like a lot of times, if you look at a manhole, if the manhole on the ground is in concrete, quite often you get like cracks coming out from the corners, because you're meant to put like a reinforcement bar around to try and stop the concrete from expanding that way. And this is why these reinforcement bars are in place. Nice thing about Wrigley tin is that underneath you can get you've got these wires that you can attach your false ceiling to. So this ceiling is just holding up these lights, and these have been sort of drilled into the concrete floor. But you can get fixings that you can just snap into place into the Wrigley tin underneath, or sometimes the Wrigley tin has holes in, so that when you're up above, you can get these straps that you just feed through little holes, and then and if you looked underneath, you'd see all these straps coming down. You can attach all of your surfaces quite easily underneath the Wrigley tin. They tend to hide Wrigley tin. I think you saw a video before of that's a power float. You've got your concrete, and you let it go off. And if you need a nice, flat, shiny surface, you can sit on that and drive around, and it polishes the top of the concrete. The students went on a placement, not a placement, a site visit. Have you been on a site visit yet? No. We went on a site visit to a school, and they had put concrete across the whole of the floor. And then they went across with a power float, which made it nice and smooth. But then they found out afterwards that the type of tile that they were putting down needed a rough surface to stick the tiles to. So they then had to go around the concrete and with a grinder and scratch all of the surface. Most of the times you have a smooth surface. It's just with that type of finish that you're putting on, you needed a rough surface.